There's Einstein. All right, let's go ahead and crack this one out. Here is the most basic problem for contact forces. You have two blocks here in this diagram. You have a force here that's pushing the system to the right, and it's given as 4.3 newtons. Here's M2, which is the box on the left, M1, which is the box on the right, and both these values are given here in this statement. So M2 on the box on the left here is 3.84 kilograms, and the little box here on the right side is 1.24 kilograms, and it sits on a friction surface. So part A wants us to find the contact force. Part B wants to know if switching the blocks order would change the contact force. All right, so let's go ahead and crack this out. In order to do these steps problem, it's important that you first, I think the first thing you should draw is these contact forces between the boundary of these blocks. So here, my yellow arrow here is pointing to the right because M2 is going to cause M1 to move to the right as well with it. So I'm going to call this F21, aka the force exerted by block 2 onto M1. And at the same time though, because there is an opposing force that's equal in magnitude except opposite direction, I'm going to call the second arrow F12. Putting M1 in front of M2 slows the system down, or I think it gets in the way, and because it gets in the way, it can only serve one purpose, as slow it down, aka the vector here must be opposing the system's natural motion. So the system wants to move to the right, but M1 is going to push against that. So I'm going to draw this one to the left because that's against the system's motion. All right, let's go ahead and crack this out. To do part A, I think the easiest block to look at is M1. So if you look at M1, the only reason M1 is going to accelerate to the right with M2 is because it's being pushed by M2, the contact force between M2 and M1. So M1 is going to move to the right because of F21. Again, the force exerted by block 2 onto block 1, which to the right, which makes sense because M1 is going to accelerate to the right. I do not want to look at this F12 for M1 because M1 is going to accelerate to the right. So using common sense, I want to say that I need to look at F21 because it is pointing rightward, which is what's causing M1 to accelerate to the right. So therefore, here, I just crop out the diagram. So therefore, the easiest way to find the contact force is to use the block with the least amount of force. M1 in this case has the least amount of force in contact with it. So I'm just going to carry down M1. What's causing M1 to accelerate to the right? That's the force exerted by block 2 onto block 1. Therefore, if you look at the system, one block, one force, it can't get any easier than this. I'm just going to set up Newton's second law, which is net force on M1 equals M1 times the acceleration. However, I don't know the acceleration, but I can find the acceleration super fast by just using force divided by the total mass of the system. So the system here is being pushed with this F, aka 4.3 newtons in the statement. And it's really, even though it's pushing M2, M2 is pushing M1, which means this force is really pushing both blocks. Right? So therefore, to find acceleration, I can just do F system, which in this case would just be this F that's given in the diagram. In this case, there's only one force drawn out for you, so it's pretty straightforward. The total mass would simply be 1.24 kilograms plus 3.84 kilograms. So if you punch in 4.3 divided by the total mass there, you should get a value of 0.85 meters per second square for the acceleration of both blocks. Okay, because they're touching, they have to accelerate at the same rate. Once I know that though, I can find the net force acting on M1, which is pretty easy to do. The net force acting on M1 is simply just F21, which is the contact force between the two blocks. So instead of saying sigma Fm1, I can substitute that in for what the actual force is in this case. So the force that is causing M1 to accelerate to the right is the contact force exerted by block 2 onto block 1, which is pointing to the right. I know M1 is 1.24 kilograms. I know the acceleration I just found is 0.85 meters per second square. And punching that in your calculator, you should get a value of 1.05. So even though I found F21, really I also found the magnitude of F12 because F21 is pointing to the right, but F12 is pointing to the left, but they have the same magnitude. And it didn't specify which force in part A. It just says find the size of the contact force. So I would assume that it just asks us to find the magnitude. So therefore, I'm just going to make the statement. I found the magnitude of the force exerted by block 2 onto 1, which is 1.05, which is the same as the magnitude of 1 onto 2, which is 1.05. So that would be my proper response for part A. I would say that the contact force between the two blocks is 1.05 newtons. Now, that's the easiest way to do it. In case you want to use the perspective of M2, to do M2, you just have to incorporate an additional force. So here, what's causing M2 to move to the right is this force that's drawn in the diagram, which is called F, which is 4.3. And then, however, if you look at this diagram properly, placing M1 in front of M2, again, causes the system to slow down. It will imply that there is an opposing force. So if you're going to look at M2's perspective, you need to incorporate this force pointing leftward, because M1 is going to cause the system to slow down or accelerate at a lesser rate. So therefore, I'm going to draw this F of 1, 2 if I'm looking at M2's perspective. And then from here, as you can see, it's one block with two forces. F is going to cause it to accelerate to the right. F1, 2 is going to cause it to slow down a little bit. So we can just set up Newton's second law for M2, which is M2A. And then we can expand sigma F here into two terms. Because again, if you look at this particular box, there are two vectors, one pointing right, one pointing left. F is going to cause it to the right. F1, 2 is going to oppose it. So I'm going to subtract that. Therefore, I can just plug values in. To solve for F12, I'm going to move this negative term to the right side, because the whole point of part A is just to find the contact force, aka F12 in this particular setup. And then to move M2A to the left side, it changes sign. So here, all I did was just isolate for F12 by just moving things around. Okay, we know what F is, we know what M2 is, we know what AX is because we already found it using the first strategy. So F here, I substitute in for 4.3 newtons because the statement said so. And then M2 is giving us 3.84 kilograms. The acceleration we found is 0.85 meters per second square. So you punch that all in your calculator and take the difference, you'll get a value of 1.04 newtons. Now I know 1.05, 1.04 is not exactly the same, but there is rounding in this particular problem. Okay, so that's that. All right, let's do it. So the same answer. I would choose the first strategy because I think it's the easiest way to go. Okay, so in this case, I would choose this perspective because it's one block with just one force. So that is the easiest perspective. So hopefully as you practice, you know which block to look at based on it's the least amount of work to get to the answer. All right, let's do part B. Part B asks us, will the contact force between the blocks be affected if the two blocks are switched? So here I swapped out the blocks. Instead of M1 being on the right side, I put it on the left side, and then I move M2 to the right side. Okay, so let's go ahead and crack this out using mathematics, and then hopefully I can touch on it just using common sense. All right, so in order to do this, we have F12 now. It's going to cause M2 to accelerate to the right, and then at the same time though, placing M2 in front of M1 again causes the system to slow down. So here I just put the contact force of block 1 onto block 2 because the placement is swapped, and then M2 now is going to oppose M1's motion. So here we say the force of block 2 onto M1. To find this particular contact force, to make sure whether we can prove the statement, I'm going to look at M2. So here's M2. What's causing M2 to accelerate to the right? It's the force exerted by M1 onto 2. So again, it's the block farthest away from the applied force. In this type of scenario, it's going to have the least amount of force. So I'm going to go ahead and look at M2 just to save some time here. What's causing M2 to move to the right? It's the force exerted by block 1 onto block 2. Therefore, I can just set up Newton's second law for M2. But in this case, the only force causing M2 to accelerate to the right is the contact force between block 1 and block 2, which I have substituted here. So here is sigma F for block 2, but there's only one force acting on it, which is the contact force exerted by M1 onto M2. Here, mass 2 is 3.84 kilograms. The acceleration has to stay the same. The force hasn't changed. The mass of the system hasn't changed. So therefore, the acceleration of the system must stay the same. Okay, so you notice here the acceleration stays the same because I don't have to redo any work. The applied force hasn't increased or decreased, and the mass of the system has remained the same. We're just swapping the blocks order. All right, so if you do that properly, you should get 3.26 Newton. Okay, so therefore the contact force between this boundary here between M1 and M2 is now 3.26. So if you kept up with part A, we found the contact force F21 and F12 to be about 1.04, 1.04, oh, excuse me, 1.05 or 1.04. But here we just found the same contact force to be 3.26. So has the value changed? Of course it has. It went from 1.05 to now 3.26. So therefore my conclusion is that yes, the contact force between the blocks changes when the blocks are switched, which make sense. Using common sense, here's M2, okay? In order to accelerate this mass, which is 3.84 kilograms at the same acceleration, this contact force here must increase in order to fit that acceleration, which makes sense to me, okay? In order to get a heavier mass, in this case M2, to accelerate at the same rate, you must push with more force, which would suggest that the contact force must change in order to keep that acceleration condition the same, okay? All right, other than that, I hope that helps. Stay nerdy, don't be whack.